good stuff. So let's see here. Let's look at this first one. If we're taking the derivative of the also here's the attendance form. If you need it, you can grab it. Actually, I'll put it here somewhere. If you need to scan it, get it later, so you can. So finding the derivative of the natural log of some stuff. Our derivative is going to be 1 over all that stuff. And of course, we're going to multiply by the derivative of that stuff. Derivative of x to the 7th is 7x to the 6th. The derivative of e to the x is e to the x. And the derivative tangent of x is secant squared of x. For this second one, I should have called it g of x. I would probably rewrite it. I would write it as g of x equal to sine of x cubed times e to the x, all raised to the 6th power. So that then when we start using the chain rule, we can say, okay, I've got some stuff to the 6th. So my derivative is going to be 6 times all that stuff to the 5th power. But then we have to multiply by the derivative of the inside stuff. So I have to take the derivative of sine of some new thing. So I know the derivative of sine of x is cosine of x. So the derivative of sine of some new stuff is going to be cosine of that new stuff multiplied by the derivative of this new stuff. So it's a multiple chain rule problem. And then finally, the derivative of x cubed times e to the x, we have to use the product rule for. So it's going to be the derivative of x cubed times e to the x plus x cubed times the derivative of e to the x, which is e to the x. Kind of lengthy, but not too terrible. Questions about any of what we did there?
Now I have a question.
Yeah, go ahead.
So for the first problem, is it possible you just put 7x to the square, that whole second part, you just put it on top of the numerator?
Yeah, totally. And people often do. I kind of like to write it out to the side because I feel like it kind of emphasizes the chain rule nature of the problem, which is that you do the outer derivative, you leave the insides alone, and then after that you multiply by the derivative of the inside. But yes, you could totally rewrite this as 7x to the 6th plus e to the x plus secant squared of x, all divided by x to the 7th. Plus
So I have another question. Since
Sure.
they're both the top and the bottom have ex, would they cancel each other out?
They do not cancel out.
They do not cancel out.
So it
Okay.
kind of be like, so it's kind of like if you have, I'm gonna write something kind of silly, right? If I have like 2 over 2 plus 5, that's 2 7ths. And I definitely can't cancel those 2's.
Okay.
It doesn't equal what, 1/5. So the only way you can cancel things in a fraction like that is if they are multiplied by other stuff. So for example, on the other hand, if I had, I really shouldn't be canceled. If I had, like say 2x plus 4 over 16 plus 8x cubed, I can totally factor out a 2 from the top and 8 from the bottom. And then the 2 and the 8, I can cancel out a 2 there. So I say I can cancel a 2 here, cancel a 2 here. So I'm left with x plus 2 over 4 times 2 plus x cubed. But I can't cancel that 2 there or an x there. We can only cancel things when they're multiplied by.
Okay. Thank you.
That's what I just think about it. Yeah, good question. All right. Other questions? There's never enough space to do this. Question, how are sitting these desks? Like, not that I can change anything about it. The reason I'm asking is because our department might be getting new desks at some point, and these are one possible option we have. So I'm just curious, how are they? Like, they're fine to sit in? Bless you. Okay, I mean, they're kind of weird, they move around, but we'll see. Good to know. Good. All right. Oh yeah, there's lots of logarithmic things to talk about. Okay, so let's do more examples. So let's say we want to find, so let's say we have this following. So f of x is the natural log of x to the 10th power plus, bless you, the natural log of x to the 10th plus the natural log of 6 times e to the x cubed power. And something to keep in mind whenever you're dealing with logarithms and their derivatives is often you are able and encouraged to simplify the logarithmic expression first. So two of these pieces can be simplified. This first piece can't. Natural log of x to the 10th you're stuck with. It is what it is. But these other two pieces, we can use the rule of logarithms where you can bring the power down here. So that can be 10 times natural log of x. And here I can use the product rule for logarithms, which is that if you have the natural log of something times something else, it's going to be the natural log, of the first piece plus the natural log of the second factor. And we should simplify more because we can. Specifically, I can bring this x cubed down in front. This is going to be the natural log of x raised to the 10th plus 10 times the natural log of x plus the natural log of 6 plus this x cubed comes down in front and left with the natural log of e. Can anyone tell me what the natural log of e is? 1. Right, it's 1 because really that's log base e of e, right? It's kind of like how, log base 6 of 6 is equal to 1, or log base 10 of 10 is equal to 1. Log base e of e is also equal to 1. Bless you. I won't say it every time, but got a lot of sneezes. Bless you. So this is just 1. So now we haven't differentiated at all, right? All we've done so far is simplify. Now we're finally ready to differentiate. And what I want to kind of stress here is that if you are simplifying something, you should only be doing that, right? If you're asked to take the derivative, you shouldn't differentiate part of it and simplify part of it. You want to do all simplifying, and then when you're ready, then differentiate it. So now we're ready to differentiate. We write the derivative, and let's see. I've got some stuff raised to the 10th power. So its derivative is 10 times my stuff to the 9th times the derivative of the inside stuff. And the derivative of the natural log of x is 1 over x. And then I have 10. Constant multiples just hang out. So if you have a constant times a function, that constant sticks around, and the derivative of your function gets multiplied by it. And the derivative of the natural log of x is 1 over x. What's the derivative of natural log of 6? It's not 1 over 6. It's 0. Because the natural log of 6, although it's kind of a weird number, it is a constant. Right? Natural log of 6, there's no variables there. I don't see an x. Do you see an x? I see no x's. There's no variables there, meaning it's a constant. It's, I don't know what it is. It's like 1 point something. Like you could plug it into your calculator and literally you would get a number that never changes. That's a constant, and its derivative is always 0. So if you see something, even though it kind of looks like a function, it's not. It's just a number, and its derivative is 0. And then over here, the derivative of x cubed times 1 is just the derivative of x cubed, which is 3x squared. I'm not huge on simplifying my answers, but I could simplify this and write it as 10 times natural log of x to the 9th all over x plus 10 over x plus 3x squared. But I really don't feel like that's necessary. Yeah. All right. Yeah, question.
Why did you do the times 1 over x for the very first part?
Because of the which rule? The chain rule. Yeah, because, right. So I'm thinking here really like this part here, if I just want to look at another example here real quick, right? If my function was something raised to the 10th power, and it could be anything, right? It could be x cubed plus, I don't know, sine of x to the 10th power. I'm thinking of that inside stuff. Well, I said it already. I'm thinking of it as my stuff. Right, this is my stuff. I'm going to say the word stuff probably 10,000 times when I teach this class. Say it a lot. So the derivative here is going to be 10 times our stuff to the 9th power. But then, of course, because we said the magic word stuff, what do we have to multiply by? Always the derivative of the stuff. 3x squared plus cosine of x in this case. Or in the previous example, we had some stuff to the 10th power, and we used the same idea. We said, oh, we're going to get 10 times our stuff to the 9th, but then we have to multiply by the derivative of that stuff. So that's what's happening there. Other questions about this one? Okay, let's look at a couple more examples. Yeah, oh yeah. Paper. Oh, wish this desk was like twice as big. It's not. I don't want to do that. Problem is if I put paper under the paper. Oh, ooh. It's a good point though. Last time I taught on one of these, I started bleeding through on this and like had kind of blue marks on the thing, which I felt kind of bad about. So maybe I should just kill some paper and live with the results. Okay, let's look at another example. Let's look at something like h of x equal to the natural log of the cube root of e to the x plus 1 over e to the 2x minus 1. Seems kind of heinous. I really, so I should say, you don't have to simplify this. You could totally take the derivative as is. I don't want to, right? If I'm going to call this my stuff for a moment, in very, very broad terms, I could say that the derivative of this is going to be 1 over that stuff times the derivative of that stuff. I'm not even writing it out because I don't want to. I don't want to take the derivative of that. That's a terrible thing to take the derivative of, to use the chain rule and the quotient rule and the chain rule. No, it's don't make your life harder than you have to. So instead, no. Simplify first. It is often in your best interest to simplify something if you can before differentiating it, especially if there's logarithms involved. Almost always, not almost always, a lot of the time with logarithms, it is meant to be simplified first. So here, I'm going to rethink of this as the natural log of e to the x plus 1 over e to the 2x minus 1, all raised to the 1/3 power. And I'm going to bring that 1/3 power down in front. So that's going to be equal to 1/3 times the natural log of e to the x plus 1 over e to the 2x minus 1. And I really don't want to use the quotient rule either, right? If I did the derivative from this point, I would be doing 1 over all this times the derivative of all that and having to use the quotient rule. But I never need to use the quotient rule if it's a quotient inside a logarithm, because I can definitely rewrite this as 1/3 times the natural log of the top stuff minus the natural log of the bottom stuff. So it's definitely going to help me avoid using the quotient rule here. So now I have 1/3 times the quantity natural log of e to the x plus 1 minus natural log of e to the 2x minus 1. And we simplify it as much as we can. There's no way we can break apart a natural log of some stuff added or subtracted together, right? That's just unbreakable. It's done, we're stuck. So now we start getting to the taking of the derivative. So let's see here. The 1/3 multiple is just going to hang out. As I like to say, constant multiples hang out. Constants on their own have a derivative that's 0. All right, derivative of the natural log of some stuff is always 1 over that stuff. What do I have to multiply by? Yeah. Yeah, I think you guys, I think it's settled in, right? It's always the derivative, okay, which is e to the x, right? The derivative of e to the x plus 1 is e to the x plus 0. And here I'm going to get minus the derivative of the natural log of some stuff is 1 over the stuff times the derivative of the stuff. Ooh, what's the derivative of e to the 2x minus 1? Yeah, or I'm going to say e to the 2x times 2, but yes, you're 100% correct. It's e to its stuff times the derivative of that stuff. And again, I don't really think we need to simplify this. You totally could write it as e to the x over e to the x plus 1 and 2e to the 2x over e to the 2x minus 1. Neither of those simplify though at all, right? There's no canceling of anything. They just are what they are. Okay. Let's, ooh, yeah, more stuff. Yeah, these are good problems. Sometimes after you haven't taught a class for a while, you're like, what did they used to do for that? Like, oh yeah, these are, when we were coming up with these way back when, they were good problems. Let's find, yeah, let's find dy dx for the following. X to the 3rd plus y to the 2nd plus the natural log of x times y equal to 7. Okay, so what words haven't I said about this problem, but are heavily implied? Right. the implicit different way. We know it's going to be implicit because you've got x's and y's all jumbled up together, right? There's no way to do this. We can't solve for y here. Literally, like you cannot isolate y and have it have only equal to things with x's in it, right? You could technically, right? You could, okay, if you're not being very careful, you could be like y squared equals 7 minus natural log of xy minus x cubed, and then square root it. But then you'd have a y in the thing that y is equal to, and that's a problem. So we can't do that. It's not going to work. We have to use implicit. All right, so again, this is where we're thinking that y is the stuff. Implicit differentiation is just kind of really a different name for using the chain rule, right? You're always thinking, oh, y is a function of x, y is my stuff. So whenever I take the derivative of like, say, y squared, I'm gonna have to multiply by the derivative of the inside stuff. X, on the other hand, is just x. Its derivative is 1. So the derivative of x cubed is 3x squared. And if you wanted, you could say times the derivative of the inside stuff, which is 1. And the derivative of y squared is 2 times my stuff to the first power times the derivative of my inside stuff. And I'll write dy dx, even though I like to write y prime. I feel like you guys like dy dx better. It's fine. Ooh, natural log of xy. So I've got the natural log of some stuff. The derivative of natural log of some stuff is always 1 over that stuff. But then we have to multiply by the derivative of the stuff, and we're gonna have to use the product rule. Right, the derivative of x. Oh yeah, question.
Could you separate ln of xy?
Oh, I totally could have. That would have been super smart to do first. Let's do that instead. So let me actually point out, I will use the product rule here just to kind of show you, but yes, that is a great observation that I should not have missed, but I did. All right. So if I was going to do it the long way though, the derivative of x times y would be the derivative of x times leave y alone plus x left alone times the derivative of y, which is dy dx, equal to 0. But yes, I agree. We should have simplified first, like I did in my notes here. So simplify first, and we have x cubed plus y squared plus the natural log of x plus the natural log of y equal to 7. And then if we differentiate, we get 3x squared plus 2y times dy dx plus the derivative of natural log of x is 1 over x. The derivative of the natural log of some stuff is 1 over the stuff times the derivative of the stuff, which is dy dx, equal to the derivative of 7, which is 0. And that's totally what you would get, right? If you distributed this to each of those, you would totally end up with what we have right here. 1 over xy times y would be 1 over x, and 1 over xy times x dy dx would be 1 over y dy dx. Yeah, good observation. Definitely, that's the way we should have done it. After you differentiate both sides in an implicit differentiation problem, you've done all the calculus there is to do. All that's left is the algebra, which is not a small thing, but it's not a calculus thing. So all that's left is grouping up the dy dx's together. So I see a dy dx here, and I see a dy dx here. That's also why doing it the second way is better, because the dy dx thing isn't like trapped with this other stuff here. It's already kind of separated, which is nice. So I'm going to leave those things on this side. On the left side, so I have 2y times dy dx plus 1 over y times dy dx. I'm going to bring the other things that are not dy dx's, specifically the 3x squared and the 1 over x. I should say that don't have dy dx's. Over to the other side, meaning they're going to change signs. I'm going to have a negative 3x squared and a minus 1 over x. And finally, well, not finally, 2 steps, I have to factor out this dy dx. So dy dx times 2y plus 1 over y equals negative 3x squared minus 1 over x. And now finally divide by that. So that dy dx is equal to negative 3x squared minus 1 over x all over 2y plus 1 over y. I will point out, this is totally how I would leave this answer. But if you were to look this answer up in a textbook, you might get something that looked more like this. You might get dy dx equal to negative 3x squared y minus y over 2y squared x plus, that's kind of dumb, James, but it's fine, x. What did I do? Well, I got rid of my denominators, and the way I did that was I multiplied both the top and bottom by xy. I'm not saying you should do this or need to do this. I'm saying sometimes the answer that we come up with is going to look different than what might be in a textbook. So if you see something that looks weird in a textbook, it might just be that they did some simplification that we are not aware of. So don't get freaked out if your answer maybe looks wrong. You're trying to look it up in the textbook. It might just be that it's written in a different format. Especially happens when you have things with logarithms. All right. No, that's a good one. Sure. So talked about the derivative of logarithms. Well, I should say we've talked about the derivative of one logarithm, the log base e. We've talked about also a little bit about the derivative of e to the x, but we also want to look at some other bases because those definitely do come up. So let's talk about how to find the derivatives of things with other bases. So let's look at something like y equal to 3 to the x squared. And actually, before we do this one, let's do a different problem. Let's say we want to find the derivative of f of x equal to e to the x squared. Well, that one's not too terrible. The derivative of e to the x is e to the x, kind of the best derivative ever. The derivative of e to the stuff is e to the stuff times the derivative of the stuff. Yeah. Right. So our derivative here is going to be e to the stuff times the derivative of the stuff. And something that's true about exponential functions when you're differentiating them is they always come back exactly as they are, right? If you're differentiating e to the x squared, you're going to get an e to the x squared and some other stuff. If you're differentiating a 3 to the x squared, we're going to end up getting a 3 to the x squared. And, excuse me, some other stuff. Okay, so there's a couple ways of dealing with this. And I don't know which way your professor is going to teach it. I'm going to show you the way that I usually do it because I think it's the best. And I can also talk about the other way of doing it, which is not terrible, it's just different. So one way of doing this is using what's called, I guess we're going to use implicit, yeah. But first we're going to take the log, the natural log of both sides. And the reason we're taking the natural log of both sides is to get that variable x squared out of the exponent. We take the natural log of both sides so that we can then bring the x squared down in front. That's a very common technique. Like if you're ever trying to solve for something and it's trapped in the exponent, we often take the natural log of both sides to get it out of there. Because then I can write this as the natural log of y equals x squared times the natural log of 3. And now both sides are things I know how to take the derivative of. All right. I want everybody to write down the derivative of the left-hand side. Write down the derivative of the natural log of y. Of course, yes. So just in general, you never have to ask me to be excused. You can totally, if you need to leave for whatever reason, you're always welcome to take off. Yeah. Yes, you may be excused. So the derivative of the natural log of y is 1 over y times dy dx. It's implicit, right? Y is a function of x. Literally, there it is. Y is a function of x plus u. So when I take the derivative of the natural log of some stuff, I get 1 over my stuff times the derivative of my stuff. All right. The other side, I feel like always throws people off a little bit. What's the derivative of x squared? What's the derivative of, let me ask you all over here. What's the derivative of 7x squared? Right, I'm going to say 7 times 2x, but yes, you all, I know what you all are saying. So the derivative of a constant times x squared or a constant times a function is just that constant times the derivative of that function. We have a constant times x squared. And the derivative is 2x times that same constant. Or, if you prefer, you can think of it this way. If I want to find the derivative of x squared times natural log of 3, I could use the product rule. If I take the derivative of this using the product rule, okay, derivative of x squared is x squared, this is not x squared, derivative of x squared is 2x. I leave the other piece alone. I add, and then I switch it up. I leave x squared alone, and I multiply by what's the derivative of the natural log of 3?
Yeah.
It's 0, right? Because it's a constant. Its derivative is 0. So we get 2x times natural log of 3. So whenever you have a function times natural log of a number, I know it feels weird. It feels like natural log of a thing is a function, but it's not here. It's really just a constant. And so when you have something like x squared times natural log of 3, the derivative is 2x times natural log of 3. All right, we're almost done. We're going to find the derivative. So I'm going to re-isolate this. I'm going to multiply back y on both sides. So dy dx equal to y times 2 to 2x times natural log of 3. But then I'm going to substitute back in what y is equal to. Right, y is 3 to the x squared. So I'm going to say that my derivative here, dy dx, is 3 to the x squared times 2x times natural log of 3. Kind of cool. We'll do one more and then we'll talk about the pattern. Okay. So let's try one more. Wish this piece of paper was bigger. Okay, so I'm gonna leave this up here for a second. Let's try taking, let's say for y equal to, say 7 to the sine of x. And again, just for comparison's sake, when we get there, I'm going to point out that the derivative of e to the sine x is e to the sine x times the derivative of sine x, which is sine x. Okay, well, let's do this one. So we're going to do the long way still, although you might already know what the pattern is to find the derivative of this, but I'm just going to do it the long way. I'm going to take the natural log of both sides. Natural log of y is the natural log of 7 to the sine of x. That allows me to bring the sine of x down in front. So natural log of y is sine of x times the natural log of 7. By the way, this process is called logarithmic differentiation, where you take the natural log of both sides, and then when you simplify the right hand side, and then the derivative of the left hand side is just 1 over y times y prime. So now we're going to differentiate. The derivative of the natural log of y is 1 over y times y prime, or dy dx. And then on the right hand side, okay, everybody take the derivative of the right hand side. Hopefully that's what you got. Okay, so on the left hand side, the derivative of natural log of y is 1 over y times dy dx. On the right hand side, the derivative of sine of x times a constant is just cosine of x times the same constant. The constant multiple hangs out. Okay, so then we solve for dy dx. Dy dx equals y times cosine of x times natural log of 7. But y is just this. So dy dx is really 7 to the sine of x times cosine of x times the natural log of 7. So for both these problems, you don't actually have to do it this longer way, where you take the natural log of both sides, you simplify, you differentiate, solve, and bring it back over. What we see in both of these problems, at least what I think we see, is I know the derivative of e to the stuff is e to the stuff times the derivative of the stuff. And in both of these problems, I'm seeing that for something like 7 to the stuff, my derivative is 7 to the stuff times the derivative of the stuff times the natural log of 7. Or for this previous problem, when my function was 3 to some stuff, my derivative was 3 to the stuff times the derivative of the stuff times the natural log of 3. It always works out that way. So in general, paper, actually more paper. If I have, come on, sorry. If I have, say, I'm gonna write this a couple different ways. If you have the derivative of a to the f of x, you're going to get a to the stuff times the derivative of the stuff times the natural log of your base. That is how it generally works. And that's also true if your base is e, right? If your base is e, the derivative of e to the stuff is e to the stuff times the derivative of the stuff times the natural log of your base. But the natural log of e is just 1, so we never write it. So it's really the same rule. Yeah, that's kind of it. Well, that's not it. I mean, that's not the story. So for example, now instead of doing that whole process, we could say, I'm going to differentiate 7 to the tangent of x by just saying, oh, well, I've got 7 to some stuff. It's going to be 7 to that same stuff times the derivative of that stuff times the natural log of the base. So this is kind of an extra little piece at the end where you multiply by the natural log of the base, which you wouldn't do if your base was equal. So you also try this one. Find the derivative of 2 to the x cubed plus x. Try that one. All right. I got 2 to the stuff. So just like every time with an exponential, the function you start with shows up in your answer, right? Not altered in some other way, shape, or form, right? You don't subtract 1 from the power or anything like that. It's just the same thing again. So whenever I see a function where the exponent has variables in it, I always know that same exact thing is going to be in my answer. You can just copy it down if you want. So there's some functions where there's more involved before you should really just copy it down, but you could technically. And then I'm going to multiply by the derivative of the stuff, which is 3x squared plus 1. And then I'm going to multiply by the natural log of the base, which is natural log of 2. That's it. Transfer. So questions about this process before we move on to something similar but related, but different. Yeah.
The final answer, so 3x squared plus 1 would not be there.
Yes, we have to include the 1. Yeah. And we do need the parentheses around that. Otherwise, it looks like if I forgot the parentheses, it would kind of look like 2 to the x cubed plus x times 3x squared, and then plus 1 times natural log of 2, which is definitely not the same as 2 to the x cubed plus 2 to the x cubed plus x times 3x squared plus 1 times natural log of 2. So parentheses are pretty vital when you're using the chain rule. They're not as vital if the derivative of your inside stuff is just 1 term, but if the derivative of your inside stuff is more than 1 term, you almost always need them. Yeah. The only time I'm not writing something is if it's 0. Yeah, good point. So in the same sort of vein, what about logarithms with different bases? So what if I said I wanted to take, I don't know, the derivative of y equal to log base 4 of x to the 7th plus 3x squared. Well, there's a lot of ways you could do this. One way would be to use the change of base formula, which is what some people will do. But it's more interesting if we do it this other way. So I'm going to rewrite this. So rewrite as an exponential equation. Oh, rewrite as this. So what's my base? This is my base. 4 And what's it being raised to? That's actually not what it's being raised to. So let me remind you all, because logarithms used to really trip me up. I always think of this equivalence. What is log base 2 of 8? Right, log base 2 of 8 is 3. Because what a logarithm is really asking for is what exponent do we need to get from this base to this answer? Oh, 2 to that exponent equals that number. And that's equivalent to what I just said. 2 to the third equals 8. So whenever I'm trying to take a logarithmic expression and change it into an exponential equation, I'm always thinking, okay, there's my base raised to whatever the logarithm is equal to, because the logarithm is an exponent. And then all that's going to equal whatever's inside the logarithm. So here we would have 4 raised to the y equal to x to the 7th plus 3x squared. And now that we just learned how to take derivatives of exponentials whose bases were not e, we can totally just use that rule. So now we're going to differentiate both sides. So the derivative of 4 to the y, or the derivative of 4 to the stuff, is going to be 4 to the stuff times the derivative of the stuff times the natural log of 4. The right-hand side is power rule. Derivative of x to the 7th is 7x to the 6th. Derivative of 3x squared is 6x. Okay, I'll remind you, I'm trying to find the derivative of y. So everything else I don't need on that side. I need to divide by it. So I have that dy dx is equal to 7x to the 6th plus 6x divided by 4 to the y times the natural log of 4. But wait, 4 to the y is what this is equal to. So all of that gets to go down and replace what 4 to the y is. So here's the thing. This is actually kind of important. If you're starting off with y as a function of x, your derivative better be in terms of just x. So for our derivative to have a y in it means we can't be done yet. We have to keep going until we're able to write it just in terms of x. That's not true if it's implicit, like in a normal implicit problem where you've got x's and y's jumbled together. It's totally fine for your derivative to be in terms of x and y. But if you're starting off with y as a function of x, we should be able to write our derivative as a function of x without y's in it. So let's see. This is going to give me dy dx equal to 7x to the 6th plus 6x over x to the 7th plus 3x squared times the natural log of 4. Okay. So here's what I'm seeing. We'll see it one more example, but I'm going to say it right now. I'm seeing, if I'm looking at this as log base 4 of some stuff, I'm seeing 1 over my stuff times the derivative of my stuff divided by the natural log of the base. And that's not a surprise, or that's not a coincidence, I should say. Let's look at one more example, though, just to kind of, let's see. Yeah, we got time. We got enough time. Let's look at one more example, and then we'll clarify this rule as well. So let's say I have, that's gnarly looking. Let's say we have y equal to the log of e to the 2x plus secant of x. Wait, what's my base? There is a base there. I didn't write it because I'm lazy and like we don't write that base. What base is the one that we don't write? It's base 10. Right? We're kind of a base 10 world in a lot of ways, not always, but base 10 is kind of like the next most common base after the natural base, base E. So to that end, we often don't write the 10 because trying to save on ink, we don't want to write it in all the textbooks, we're just lazy. So yeah, if someone says log, they mean log base 10. Except for one terrible math professor who says that that's natural log. You guys don't have him though, so you're like, he's not terrible. He just, this is one terrible thing he does. So in upper division math classes, sometimes they say that log, L-O-G, is the natural log because people like to be mean, right? Like, why would you do that? Why are we going to change the anyway? So just in case you have Professor Mulassi at some point, which you probably won't, because I don't think he teaches the 16 series usually. But if you ever do, just be aware that he might write log and mean the natural log instead of the log base 10. But no one else is mean and does that, so you shouldn't worry about it. But I just couldn't help myself from saying that. It popped into my head. So we're gonna do the same thing. This is y equal to log base 10, and we're gonna rewrite it. We're gonna rewrite as 10 raised to the y power equals e to the 2x plus secant of x. And then we're going to differentiate both sides. So the derivative of 10 to the y, or more generally, right, a to the f of x, the derivative is a to the stuff times the derivative of the stuff times the natural log of a. So here the derivative of 10 to the y is 10 to the stuff times the derivative of the stuff times the natural log of the base. On the right hand side, straight up regular derivative rules. Oh, I've got a chain rule on the right hand side. I've got e to the 2x whose derivative is e to the stuff times the derivative of the stuff, which we usually write the 2 in front. And then the derivative of secant of x is secant of x times tangent of x. And now, just like before, we're just trying to solve for that. So I'm going to get that, excuse me, dy dx is 2e to the 2x plus secant of x times tangent of x over 10 to the y times the natural log of 10. Of course, we're not done because we're going to replace 10 to the y with e to the 2x plus secant of x. So really we have dy dx is equal to 2e to the 2x plus secant of x times tangent of x over 10 to the y, which was e to the 2x plus secant of x times the natural log of 10. And I will say once again, just like in the previous problem, we have the same sort of pattern. For our function that's log base 10 of some stuff, what we're getting is 1 over that stuff times the derivative of that stuff divided by the natural log of 10, or the natural log of the base. So it's kind of interesting. For exponential things like the ones we did before, like 2 to the x or 3 to the x squared or whatever, you end up multiplying by the natural log of whatever the new base is. Whereas for these logarithmic ones, instead of multiplying by the natural log of the base, you end up dividing by the natural log of the base. It's kind of neat. So let's write down these rules. So if you have, so let me be consistent about how I'm writing things here. Sure. So if we were taking, say, the derivative of, I want to make sure I'm being very consistent. 1 second, I'm sorry. Okay, sure. So if we're taking the derivative of the log base a of some stuff, it's going to be 1 over the stuff divided by the natural log of a times the derivative of the stuff. Or people probably prefer to write it in a more compact form. We could really write it as derivative log base a of some stuff is the derivative of the stuff over the stuff times the natural log of a. And again, I will just point out, this is also the rule if your base is e. The derivative of the natural log of some stuff is the derivative of your stuff over your stuff times the natural log of e. The natural log of e is just 1. So these are the rules for taking derivatives of things with different bases. And essentially, if it's exponential, the additional step is to multiply by the natural log of the base. If it's logarithmic, the additional step is to divide by the natural log of the base. That's kind of it. Let's see. We got a minute. No, let's not try to cram more stuff in. I don't need to cram more stuff in. I think that's a good stopping place. Let's stop there with a few minutes left over. That's fine. It's not a crime. And last